In this video, we're going to talk about testing linear correlation. Let's look at some definitions. So what is testing linear correlation? It's a way to determine if there is a significant linear correlation between two variables in the given sample of order pairs. What is correlation? A correlation between two variables is when there is an apparent association between the values of one variable with the corresponding values from another variable. Linear versus non-linear correlation. In this picture on the left side, the order pairs appear to have a linear relationship, where on the picture on the right side, the points do not appear to have a linear correlation. So what is linear correlation? The linear correlation is defined when the ratio of two given variables, usually x and y, are almost the same for all the points in the sample. What is linear correlation coefficient? The linear correlation coefficient is a numerical value that measures the strength of the linear correlation between the x and y, and it's usually shown by letter R. What are the properties of linear correlation coefficient R? Well, R will be always between -1 and 1 inclusive. It is designed to measure the strength of only linear relationship. R is significant and changes value if the sample contains any outliers. The linear correlation coefficient is considered significant when absolute value of R is fairly close to 1. So now let's talk about how to compute R. We find summation of x, summation of y's, summation of xy, summation of x squared, and summation of y squared. And now here is the formula. In this formula, n represents the number of ordered pairs. In most cases, R is usually calculated with the computer software or a calculator. In this example, the study time and the midterm exam scores for a random sample of 10 students in a stat course are shown in the following table. So student studied 3 hours, got 57. Student studied 4 hours, got 65. Another student studied 4 hours and got 72, and so on and so forth. We want to find the value of the linear correlation coefficient R by using the formula. First, we're going to store all the x values in L1 and all corresponding y values in L2. Then we're going to use ti command 2 var stats to find summation of x, summation of y, summation of xy, summation of x squared, and summation of y squared. In this example, as we mentioned earlier, n was equal to 10. Now we're going to apply these values in the formula for R. We do it piece by piece. And finally, R in 3 decimals is approximately 0.959, which is very close to 1. Now, testing process for linear correlation. Setting up HO and H1. The null hypothesis will be rho equal to 0. That implies that the linear correlation is not significant. And in the alternative hypothesis, rho is not equal to 0, which implies that the linear correlation is significant. We're going to use TI commands or formula to find a p-value for two-tailed test. By p-value method, if p-value is less than or equal to alpha, then H1 is valid, meaning linear correlation is significant. And if p-value is greater than alpha, then HO is valid, which implies linear correlation is not significant. And as usual, the final conclusion should be about, in this case, whether the linear correlation is significant or not. So using the last example that we just talked about, we want to use TI command linear regression t-test to find CTST, p-value p, and linear correlation coefficient R. So of course, we're going to store values of x in L1 and values of corresponding y's in L2. Then we're going to go to stat, tests, and arrow down to linear regression t-test, where x list is L1, y list is L2, frequency is 1, and we choose rho not equal to 0, and we also make sure that the regression equation option is blank. So the screen should look like this: x list L1, y list L2, frequency 1, rho not equal to 0, regression equation blank, and then you press calculate to view the results. So the CTST will be 9.626. The p-value is in scientific notation. And if you arrow down, you're going to get more values, such as A, B, R, and R squared. So the CTST is 9.626. The p-value is 1.1 times 10 to the negative 5. And the linear correlation coefficient, as we found it by using the formula, is 0.959. We can also find the equation of the regression line. y equal to a plus bx, or y hat equal to a plus bx. Based on the results we have, a is approximately 46, b is approximately 5, so the regression equation y hat is approximately 46 plus 5x. How to find the CTS using the formula? The formula for the CTS comes in different form. This is one version of it. T is equal to r times square root of n minus 2 over 1 minus r squared. So in this example, we have n equal to 10, r is equal to 0.959. We want to find the CTS by using the formula and the corresponding p-value. Plug in the values. Simplify. Simplify more. And our CTST is 9.59. To find a corresponding p-value, we're going to use TI command tcdf with the degrees of freedom n minus 2. Since this is a two-tailed test, we're going to multiply that area by 2. So we add the CTS 9.59. So p-value will be 2 times that area, which becomes 1.16 times 10 to the negative 5. Again, it's in scientific notation. Now let's look at this example. The same example that we used earlier. We want to use p-value method at 0.05 significance level to determine whether the linear correlation is significant or not. We set up HO and H1. HO rho equal to 0, meaning linear correlation is not significant. H1 rho is not equal to 0, linear correlation is significant. Our p-value is less than or equal to alpha. Then in this case, H1 is valid, which implies linear correlation is significant. The conclusion whether the linear correlation is significant or not is an important factor as we move forward. That allows us to make predictions. I hope this video helps you understand how to test linear correlation coefficient and determine if the linear correlation is significant or not.